Thank you very much for the introduction. So as I take the first part, you will take a couple of minutes to seat and come back later on. So stick slip. Who has ever had issues with stick slip in the audience? So I see some hands going up, then we are right with the topic. I will do the things a bit more easy to understand stick slip. Examples we have here, we have a grasshopper, for example, you know the noise, the vibrations. We have some basketball shoes. If you listen to a basketball play, you sometimes have the noise. And what I enjoyed in my childhood a lot is singing glasses. And at the end, it's all about vibrations. So now I need a bit assistance coming to my experiment to demonstrate what is stick slip at a simple way.
Keep going.
And you even can see it swinging off the water. And to make it simple, you can say the fluid in our hydraulic cylinder is the water. My finger is the seal, and the counter surface is the glass. And to demonstrate how sensitive the system is, I only change a bit the filling of the glass and do the same again. So the noise is completely different. So this is at the end nothing else than inducing vibrations. And if you do this, thank you for the assistance, in a hydraulic cylinder or a hydraulic application, you even can bring the whole system to swing, which of course nobody wants to have. So coming to the basics. At the end, it's all about the changing of the movement. It's motion and stop, stick and slip. So we have at least two important coefficients of friction which come into play. It's the static coefficient and the dynamic coefficient. And the change is then μs, the static one, is bigger than the dynamic one. And at the end, which Christoph will explain much better later on, from the academic side, there's no clear idea on understanding the principle of stick slip. What's about? We all talk about friction. What we have the dry friction, we have the mixed friction, and we have the dynamic friction. For sure, what we all love is the dynamic friction. But if we begin a movement, we need the change of static mixed to dynamic friction. Looking into the Streiber curve, you have the boundary friction in the area 1, we have the mixed friction in the area 2, and then we like to have the dynamic friction. In the area 3, we have the friction force over the velocity. And the velocity is 0, then we have the static friction. So far it's simple. If we look into friction measurements of rod seals, you see here some measurements. On the one side we have the velocity, on the other side the friction force. We look on different pressure levels now, and if you have a low velocity, so you have a little change in the velocity, 0.0 something meters per second, and you have a big change of the friction force, then the tendency to get a stick slip effect is very big. How does this look like now? Just listen to a hydraulic cylinder. Here we have it. So this is the hydraulic cylinder we simulated on a test machine. This is the noise only due to the seal. We did a very bad counter surface. We will see later on aluminum oxide coating to provoke that. And this is just the noise coming from the seal. You see the frequency is about 300 Hertz. And you see now the different directions of the acceleration we measured. So who likes that in applications? No one. This is clear. So the basics and motivation we have is that we see that especially if we have an exact positioning needed, the stick slip effect is very negative. the vibrations can lead to safety issues. If you think on a big crane and you have this stick-slip effect, the whole system can go into a swinging situation. And we have this unwanted noise and also wear in the sealing system. And this occurs due to the relative movement of the seal to the rod. So I will hand over to Christoph now, as we come now to the theoretical part of the simulation of stick-slip.
Thanks, Mandy, for handing over and for giving the technical introduction into this topic. Thanks, Roger, too, for the personal introduction. Welcome from my side to this presentation here about stick-slip simulation, how to get rid of it, and about application and a little outlook. In my opinion, the example Mandy showed is very good also for this slide. When we look at the glass, you saw that also the glass, or you saw that the fluid was vibrating. That means that also the glass was, of course, vibrating, and that is what we have here. When we have resonance, our application or complete system can get in a state we don't want to have, and it can really also be a safety issue. First of all, I would like to explain it a little bit. What's the background or what's the reason behind stick-slip? So I took a picture out of the lecture Sealing Technology, which is given every year at the University of Stuttgart here nearby. And in this picture, it's quite nice explained. When we look at the left picture here, you see in this area the force goes up. So the y-axis shows the force over time. And as soon as the force goes up, it means the seal is compressed in axial direction. Due to this compression, the elastic force of the seal becomes larger, and that's why the force goes up here. This can only go up to a maximum. We see it in this picture here. When we're at the maximum force, the seal is compressed a lot, and also due to our Poisson's ratio, it is expanded in radial direction. At this point, the friction limit is reached. That means the static friction is no longer valid. The frictional contact cannot act against this high load. And this means the seal gets or will move a bit, and this means we have a relative displacement or a relative speed between sealing edge and rod. And that's why we get into dynamic friction, and the dynamic friction coefficient, especially of polyurethane materials, is much more lower. And that's why we get into a state where we have slipping, and then the force goes down because our friction coefficient falls down due to the lower dynamic friction coefficient. And then it goes down to a minimum, and during downgoing, the seal will expand again. Of course, at a certain point, the zero is again zero, because when it's no longer compressed, the seal in axial direction, we have no elastic force. And at this point, the seal will not move further, and it will again taken by the rod to the right side. So that's how the stick-slip effect works. I added one more slide to this lecture scan here, let's say, to show up the speed curves. So the black curve here is the same curve as in the diagram before. But I added the green curve here to show the speed of the point or at the sealing lip. So on the left, when we have sticking, so when the force goes up, it's stick. Then we have a constant velocity of the sealing edge, which is the same simply as the speed of the rod. So it moves together with the rod. And thinking about that, it is clear it can only work for slow rod movement speeds. So as soon as the rod is moving very fast, we don't have stick-slip. That's what we all see in reality too. And then when the maximum is reached, the speed becomes zero, because then the seal is no longer being compressed. And as soon as it begins to expand, of course, the sealing edge moves in the other direction. That's why the force becomes negative. So the dashed line here is the zero line of the speed, so it becomes negative until a minimum is reached. We don't know exactly where this minimum is, but there must be a minimum because it goes up again. When we have stick again, it has to be again the same as the rod speed. So just to think about a bit, I made this slide also for myself to get a better understanding. So there are also some interesting points. For example, the minimum here. At that point, we know we have the smallest friction coefficient because the speed or the relative speed between rod and sealing edge is the highest. Furthermore, for example, this area here has to be the same as this plus this because the lip is on the most right position, and after one period, it has to be again on the most right position. So knowing that, we thought, okay, when we would like to simulate this, what do we have to think about? One of the most important things is to model, of course, the frictional contact. And here we have to model a slip rate dependent friction coefficient. So that was something we included in our simulation model. In this example, first you see a U-cup seal. I will later on come to another seal. But here we did some first, let's say, basic trials. One more word to friction. Since friction is of dissipative character, it already dams itself, you can say. So, of course, this is the frictional contact, which is the important one. So there we put a dynamic transition or a friction coefficient which is slip rate dependent from a high static coefficient down to a small dynamic friction coefficient. And here I have a little movie showing what is happening. Maybe you can start the movie, please. So we have a rod movement here to the right. So the rod is moving with a constant speed to the right. As soon as the movie starts, you will not see the rod movement, but you will see that the sealing edge will move here. So you see the sealing edge is moving to the right now until a certain point, and now it goes back to the left. That's the point where we have slipping. Now it's again sticking. It moves to the right, and now it's slipping. So it's exactly what we expect there to happen. So the rod moves, we have stick, we have slip, and we have the transition between both. So this is made also with a polyurethane material behind it. And the next step is to go a bit more in detail. We also want to consider real values, force values, not only the picture here. And for that, we went to another product. We looked at a step seal, O-ring energized step seal, with one of our new polyurethane compounds, the Z45, and made detailed simulations on this, where we also compared to tests. So you see here the finite element discretization. You see a model overview over the step seal here. It's important we have to do a dynamic FEA here. So as stick slip is of dynamic nature itself, we have to model the fully dynamic situation. Of course, we have to consider large displacements, large deformations, because we have typical sealing materials like our elastomer in the O-ring, which is really deforming quite heavily, and we have nonlinear material behavior. We have to model these things quite correctly to get a good result out of it. Here a little overview showing the basic equation of a dynamic FEA. So there are some changes compared to typical other FEAs we do, which are often quasi-static, so do not account for any dynamic effects. So now we have to also look at the inertia forces, which are given through the accelerations of all nodes in our model, and we have to also look at the velocities here. U means the displacements, U point is the velocities, and these are the accelerations. And we have to consider the mass matrix here. So the density also plays a role to set or to clarify the inertia forces. Then we have a damping part here with a damping matrix. We have our stiffness matrix, which itself already is quite complicated to calculate, but we are happy that we have a very strong finite element software which is able to do that very well. And on the right side, we have our external loads in this basic equation, which in our case normally is the pressure. So a little picture about the general system behavior. What is quite important now is that we have such a dashboard here beside two spring elements. The spring elements are influenced by the material and by the structure, and the dashboard is also influenced by the material, but it's also heavily influenced by the friction, since friction, as I said, itself is already a dissipative quantity. And here you see a general system answer to a sudden strain load. So when we put a strain load or a displacement on this system, which is our sealing system, like this, we get a high stress peak in the beginning and then a relaxation due to viscose effects through this dashboard here. Okay, so next I would like to show you what we did concerning the frictional contact, so how we did model in general or in principle the friction here. So we said, okay, we have a static friction coefficient which is quite high, which is this one here, at a relative movement of 0, so its slip rate is 0, and when the slip rate becomes larger, it goes down like an exponential function. And in the end, in this area is not changing anymore. There we have the dynamic friction state. Mandy showed the slide with the Striebeck curve. So this is more or less the part of the Striebeck curve where we have the mixed lubrication region. So it's a bit simplified, you can say, but the nice thing is that we have one, let's say, main parameter, which is this decay coefficient here in the exponential function. And this decay coefficient allows us to model the friction behavior in the transition zone, which is very important, of course, for the stick-slip effect. So this curve has to be fitted against experimental data, and then we can model the frictional contact. Next, we have to model the material, and material modeling in sealing systems is very sophisticated, and but it's also very interesting. So there are a lot of different materials we have in sealing applications in our sealing systems. So we have, for example, elastomers which behave hyperelastic. Typical material models are Neo-Hook, Muni-Riflin, or Ogden. I made a little overview here following a scientist called Haupt, who said in general we have 4 classes of different material models: elastic, plastic, viscoelastic, and viscoplastic. And with our sealing materials, we have examples for every class, you can say. So when we look at the hyperelastic, the elastomers, like the O-ring in this example, we also, when we consider time-dependent material behavior, can model it using viscoelastic material models. On the other hand, we have elastic plastic material models typical for our PTFE compounds. So when we look at these compounds and look at time-dependent material behavior, we also have these viscoplastic material models. And yeah, it's not enough. When we look at other things, like what we often have is temperature dependency. So at TSS, we often do simulations where we consider different temperatures, and there we can do most of these models temperature dependent. So we change the temperature, and the material model is changing how the temperature goes. Then we can also have anisotropy. For example, we have seals which are reinforced by fabrics, and there we have finite element models which are anisotropic, modeling this behavior here. Also, we can have other dependencies depending on what is going on in our system. So here you have an overview what is possible in simulation at TSS. And now I would like to show some first results, and after that compare these results to test results we did on stick-slip effects. So here you see the actual force, which is measured at the rod, so the friction force of the seal. In this case, it's only one seal, because we started keeping it simple, considering one seal, also in the test, one seal without pressure, just to focus on the frictional contact at one point and to model the friction and the stick-slip effect here. So what you see here is two different rod speeds, 0.01 meter per second, and down the picture is 0.02 meter per second. And we have the outstroke and the instroke. So in both cases, outstroke on left, instroke on the right. And what we already see here is that we have a different behavior, outstroke, instroke. And this is simply reasoned by the shape of the step seal. When you look at the cross-section, it's asymmetric. That means instroke can have a different behavior than outstroke. And this already made me happy, because we see the design influence here, which gives us, in the end, or that's our goal, to know what is the design influence on the stick-slip effect, to make our design in that way that it prevents from stick-slip. So we see already the design influence, because outstroke is different than instroke. And we see, when we look at instroke, we have a quite high force amplitude. So the force is vibrating here, so that means in this case here we have stick-slip. While here the amplitude is very small, it's nearly nothing. So you can say there's no stick-slip, or just a very little bit. It's the same for this speed here, but when we look at a higher speed, at the next higher speed, which in this case was 0.05 meter per second, then the force amplitude is already decreased significantly. And that's also what we know from reality. When the rod is moving faster, we don't have stick-slip anymore. Because the sealing lip cannot follow so fast, we directly have a low force amplitude, and we cannot hear anything. So that is the first part of simulation results here. In this case, first pressureless and only one seal. And now I would like to show you the comparison to test results. So when we look at the test we did here, we made it very simple. We said we want to exclude other effects due to a second seal. We just install one seal here in our test rig, no pressure, and we move the rod very slowly. We look at different rod velocities, the same three velocities I just showed to you, and we had this rough rod, alumina coated as Mandy said it. And when we look at this test, you see the test rig here. When the rod is moving to the right, that is inwards. Maybe we can directly start the movie here, and just here. You hear now stick-slip, no stick-slip. Stick-slip, no stick-slip. So it's the same as we saw it in the simulation result. When the rod is going inwards, we have stick-slip. When it's going outwards, no stick-slip. So that already made me really happy here, that we had this general accordance to the simulation. When we look at the values, it's the following picture. We have the experiment here in gray, the simulation in black. So you see on the outstroke side, both very small amplitudes, no stick-slip. That's also what we observed during the test. On the right side, when we look at the amplitudes at the very low speed, we have a quite good accordance. Here at the next higher one, there is a gap, so we still have, let's say, room for improvement. But the outcome is the same. We have stick-slip in the simulation, and we have stick-slip in the experiment. The amplitude has a certain error here, but when we look at the next speed here, this arrow again becomes smaller. So here we have also a quite good accordance between test and simulation. So when we look at the high speed, also test and simulation showed nearly no stick slip. So that's what, there we already reached our first goal, to have the possibility to be in general able to say, to predict stick slip in our applications or products. Of course, we can improve the amplitude here, for example, for this speed, but in the end we want to prevent stick slip. It's not necessary that we exactly know the amplitude, because in the end we don't want to have a stick slip, and that's also the next thing I would like to show to you. In the team of Holger Jordan and Many Wilke was proposed this damping seal concept, where a damping element is inserted in the groove behind the step seal. So in this place here, it's made of an elastomer, for example FKM, and by using this element, the goal is to eliminate stick slip. And this slide was already shown before. So here in this case, we have again the same system behavior. We have our dashboard, we have two springs, but what I want to say here, and that's why I put this sentence here in blue, it's modified through the damping element. So the damping element changes the behavior of this dashboard, and it changes the behavior, or in the end, the parameters of the springs here, which means it does not only mean it changes the damping behavior, it also, for example, changes the relation of the axial stiffness to the radial stiffness. This is not shown here because it's a one-dimensional picture, but this relation is also very important, because when the seal is compressed axially, the radial force, of course, plays a very large role, because multiplied with the friction coefficient, it gives you the end, or it gives you the friction limit. And that's why it's very important how the relation of the stiffness is ongoing. And this is also changed by the damping element. And of course now we have a lot of freedom concerning design. We can design the cross-section here. We can choose different materials for this damping element. And so we have a lot of things where we can design how to make the system stable against a stick slip. And we can evaluate that with this simulation method. Here I would like to show you a simulation result where you see the deformation of this damping element. So you see it's quite heavily deformed. It shows that it's a quite elastic material. I said on the previous slide it's an elastomer, so it is quite soft. And yeah, that's also one thing which is important to effectively damp or erase the stick slip effect in this example. So again, I would like to show test results with this damping seal concept and with the simulation of this damping seal concept. So now we installed the second seal too, and we also put pressure onto the system. And both seals are now damping seal concept on the one side and no damping seal on the second side. So you see here in gray without damping element, you see we have a very large force amplitude. It's the same, or it's the same critical situation. It's the most critical speed. It's a 0.02 meter per second without damping element, and in black you see it with the damping element. That means the damping element works really good, as you can see here. Maybe you ask yourself why there's this difference here in the x-axis. I simply moved the curves a bit that it's easier to see where the sign changes. So in reality, there's no gap between this. So normally it's a bit shifted. And when we now go to the simulation, it looks like this. So in black, we see the simulation. In gray, we see the damping seal concept experiment. Again, for the most critical speed here, for the 0.02 meter per second. And you see, we are a little bit overestimating the average force here, but the force amplitude, so the vibrations in the end, and that's what is important, is quite good. It's more or less the same amplitude here. Also on this side, you may be a bit, you see a bit here this behavior, why the experiment goes down a bit here. That's something we are still in investigation to find out what is happening here. But in general, we can quite good predict the amplitude of the vibrations here, and we can prove that the damping seal, or we can better understand the damping seal concept here, in this case with this simulation. Okay, so with this, I would already like to conclude or to stop the simulation part and hand over to Mandy again, who will say some more words or show a little movie about the damping seal concept and give a conclusion.
Thank you, Christoph.
Thank you from my side for now.
So as I like it always very concrete and practical, I prepared a little film, and you just enjoy it. So this was a summary of what Christoph did with his simulation, you could say, coming and thinking into applications now. At least what we see as a trend also is the topic of lightweight construction, lightweight design, and of course it's obvious that then the sensitivity of the systems become even more critical. So we have lightweight cylinders. Very often we have also see the CFK topics. So a different trend in the application somehow. And it's obvious if I have a lightweight construction, the sensitivity to get noise or vibration into the system becomes more critical. And also under the aspect that the counter surface topography becomes completely different in those kind of lightweight constructions. So basically, to conclude and give a little bit an outlook, we have the possibility now to have also a simulation of the effects of stick slip. And Christoph presented very well. We have a model for that. Maybe we have to improve at some certain points, but even to simulate that is possible now. We have a comparison of test results combined with what we have in the simulation. And we showed you the damping seal concept. Maybe some remember 2 years ago we already had that idea. And now we have the transfer to the simulation also. So the outlook is also to go into new ideas with this damping seal concept.